volumetric efficiency. So we're going to talk about, so this is the how efficient the volume that is being displaced by your compressor. So we have the equation that the volumetric efficiency is equal to the volume the gas drawn, no? Drawn in. So that will be during the suction stage. Then divided by the displacement of volume. So usually class, the if you will going to represent this one. So if we have call this the now to demonstrate yung volumetric efficiency, I bring down here the piston and cylinder arrangement for our typical compressor, no? Piston displacement, reciprocating compressor, sorry. Now, usually, you have a volume displace. So when we say is the volume displace is how much farther yung displacement ng piston mo in the cylinder. So this is, for example, if we have this volume displace of our compressor here, so at this point, so ito yung total displacement niya. Okay, so showing that one here. So this will be your, say this is the BD, no? So that is the volume displace. Now, during the suction stroke or during the intake, so eventually the air will pass to your for your valves, so during the suction stroke. So hindi naman siya totally yun during suction stroke. These are not being filled by full of air. Okay, so this is partially, no? So yung dinidisplace ng piston was not being tawag dito being supply by kung ilan yung dinisplace na volume ng piston mo. So it is not also the amount of volume of air that is being sucked by the compressor during the suction stroke. So there is a part that being were not being part na yung dami ng, so the quantity of the volume of the air which is not equal to the volume of the displace. So that explains, okay? So that's why we have yung tinatawag na volumetric efficiency. So that is the volume of the gas drawn in. So how much is being drawn versus the ratio divided by the displacement volume. So that is the displaced BD. Okay? Now, if we're going to write in an equation, so we have the volumetric efficiency now natin. So we have your N, so it is represented by NV. So that is equal now to the volume of 1 during the suction stroke or initially. So which is divided by the volume displaced. So how much is the displacement of the piston? So starting from here, the top dead center, and we have here your top, we call it top dead center. So they call it top dead center, and we have your bottom, bottom dead center. So we have now, we can rewrite your equation. So that will be your B1 minus your B4 divided by the volume displaced. So if we have the cycle ng compressor natin, so during the suction stroke, so we have here initially, we have your suction stroke of for your 0.1 during the suction stroke. So this will be so that will be also your B1. Okay, so call this from starting from dito natin and going here. So this will be our B1. So this is our B1. Now during the compression stroke, so usually we have your PBN, no? So we have your 2 going up here during screw compression stroke. So we have your PB raised to N, which is your constant. Then we have your discharge, okay, okay, at the point 3. Then again, suction stroke going to your point 4. Okay. So that's why this one will be your um, B1. So in the equation, B1 minus your B4. Now for the volume displays, so how much is the being volume that is being drawn by the system? So starting from here, so here. So we have your BD. So that will be the volume displays. Now for your B1, our B1 is also from here, B1 prime. Okay. So this represents your B1 prime. So sometimes it will be given the problem, or sometimes the Boolean displays is being given to the problem. Also, sometimes your B1 will be given to the problem. Okay, so that represents yung equation natin na ito for our volumetric efficiency. So you will notice here that the Boolean BD is how much being displaced, the total volume being displaced. Then our B1 prime is only how much air starting from here is from point 4 to point 1. This is the how much air that is only being sucked by the compressor during the suction stroke. So by definition, our volume displaced is the volume of the volume swept by the face of the piston in one stroke. So that is one stroke. When we say one stroke, that is one going down here. So one stroke, that is one portion that is going down here. So that is what we call the suction stroke or one stroke. Now for our clearance ratio, so that will be the percent of clearance. So that is expressed by C. So that will be equal to the ratio of your B3 over BD. Okay, so you will notice here V3 over your VD. So that is the ratio. So at the volume at this stage, and also how much is the being swept by the piston. So that is the clearance. Then we can express our volumetric efficiency, or NB can also be expressed as 1 plus C, so that will be the clearance minus your C. So that is multiplied to the ratio of your pressure 2 minus your pressure 1. That is raised to the power exponent of 1 over N. So it can be expressed also by means of using also your clearance. Then we can express our volume displaced, your BD. So that will be equal to the area of the pistons, that will be pi over 4. Then pi over 4 d squared. Okay, so that will be the surface area of the pistons. Then we have your L for your stroke, multiply by N, then multiply by N. So N stands for the number of cycle completed per minute. So again, definition for the equation. So we have your D, so that will be the diameter. Then again, in length of stroke. Then you have your N, the number of cycle completed per minute. Then your N. So if for single acting compressors, so that will be your N. So your N is the compressor speed or the RPM to be multiplied by 1. Now for compressor that is double acting, so when we say double acting, that is I'm going to for double acting, usually the arrangements is if you have your pistons here, okay. So you have you have the suction here, then you have also another displacement for suction and displacement for this side. So you have a suction volume here, then you have also another valves here. So if the during the suction stroke, so going up, so you have to supply two volumes of air that is being displaced during the suction, and you have also the being during the suction stroke, it is also being a compression stroke at the bottom uh, of this part of the piston. So that's why it is called a double acting. So you have the suction on this side and also compression on this side. During the compression this side, you have the suction on the other side. So it is simultaneously. So opposite workingly, that is the means of your double acting compressors. Now, by definition, a single acting compressor, so that will makes one complete cycle in one revolution. Okay. Now, for double acting, so compressor makes two complete cycles in one revolution. So you will notice that one here, as I illustrate now. So for single single acting, just only one cycle completed. Now for double acting, so we have two cycles. Okay, so one here and the other one there. Okay, so that define that one. Now for our single acting compressor, so we have this piston and cylinder arrangement now. So we have here your crankshaft rotating at the RPM given to the problem, no, or stated by the RPM of the motor. Now we have here your piston and we have here your air being compressed. So this is the arrangement of a single acting compressor. So for double acting compressor, so initially in a diagram, so it will be for representation. So just for simple representation, so we have this one. Now, so we have here this part is now your cylinder. Okay. Then we shall have your piston at this part, and so this is your piston. Okay. Then we have your this one where your piston ring. Okay. Then we have here your piston rod. This one is the being going down here. And we have for the wrist pin at this pipe, this port, this part. So wrist pin, this part. Then we shall have your connecting rod for this one. So this will be your connecting rod. So the same as also we have in internal combustion engine. No? Then at this part also we have now your call this crankshaft. So this will be your crankshaft. That will be rotating, no? Okay. So if you're going to look the industrial type, so referring to this one, so they are for industrial type. So this is how it looks like when we do a cross-sectional view. So this is also a double acting compressor. So you will notice here, so it is sealed back here. So but it is also a double acting type. Now for ease of representation for solving, so we do this type of arrangement. Okay, but in industrial, so it is already look like this. Okay. Okay, so we have a sample problem. A twin cylinder double acting compressor with a clearance of 5% handles a 20 cubic meter per minute of air, sorry, that is of nitrogen from 100 kPa uh, at 37 degrees Celsius go compressed to 725 kPa. Then we have the compression expansion are on the polytropic process with N which is equal to 1.30. So find A, we have your work and how much is the heat being rejected and what will be the bore to stroke ratio, bore to stroke for the given RPM, which is 150, and we have your length over your length over the and L over D, that will be the length of stroke over your diameter of the piston, which is equal now to 1.3. So first things first, so we need to establish what are the unknown of the problem. Sorry, the given of the problem. So again, reviewing here. So we have the initial volume. We have your during the suction B1. Okay, so this is the B1 prime. So our B1 prime here, or the volume flow rate 1, so that will be equal to, so we have 20, no? 20 cubic meter per minute. Then you will notice here we have a given C for your clearance, so that will be 5%. Yes. Then we have during the suction stroke, so that will be your P1, is we have 100, no? 100 kPa. Okay. Then we have the temperature also at the same time corresponding during the suction stroke. So we have your T1, which is at 37 degrees Celsius. Okay. So I'm going to add here the 273 to convert it already to Kelvin. So we have 310 Kelvin. Okay. Then given also we have for your P2 during the compression stroke. So we have the 725. So that will be your kilopascal. So the temperature at that point was not given to the problem. So your T2 is unknown. Okay. Then also we have this one. So it is a polytropic process. So take note of that one where your N is equal to 1.30. And also given we have your RPM. This is N, no? So this is N for the polytropic process 1.3. Uh, so I'm gonna write here a polytropic process so we can distinguish to the N versus the N that we're using for the RPM polytropic process. Then we have your N for your RPM. So that will be the revolution per minute of the rotation of your crankshaft, which is 150 revolution per minute. Then we have also given the ratio of length to bore, or length of the stroke divided by your diameter or bore of the cylinder or the piston. So we have the ratio of that one, which is equal to 1.30. Okay. So almost the same the value of your N. So for the unknown of the problem, so start with letter A. Okay. So we're looking now the work. So what will be the work of the compressor here? So we have your work of the compressor. Now for the equation for the work of the compressor, so we have the equation for polytropic process. So that will be equal to N, no? So that will be your P1, B1 ratio of 1 minus your N. Then this is multiplied by the ratio of pressure 2 over pressure 1 to the power, or to the exponent of N minus 1 over N. That will be minus 1. Okay. So looking at that, so if let's check if we can compute now the work of the compressor. So N, we have the value of your N, that will be 1.3, and for your piece of 1, we have for initial pressure we have your 100 kPa. Volume 1, so we can use this one, so that will be 20 cubic meter for initially. So it is okay, it's okay, we have given for this one. For pressure 2, we have 725, okay. So, and pressure 1, okay. Then the value of N, which is 1.3, okay. So we can directly solve our equation and just substitute now our given uh, given data. So I'm rewriting now our equation, work of your compressor. So the value of N, that will be 1.3. So that will be the multiply by the pressure 1. We have 100 kPa, then multiply by the, so I'm gonna express this one, so to how, so in order to we can cancel the units here, so I'm gonna express this one to kilonewton per square meter. Then our volume 1, which is given to the problem, that will be 20, okay, 20 cubic meter per minute, okay, then divided by all over, saying that will be all over by 1, okay, minus n. So take note, we have to distinguish this one. The other n, this is for revolution per minute, and the other n that will be using for polytropic process. Take note of that one. So 1.3. Then we shall multiply this one to the ratio of your p sub 2, where p sub 2, so we have the 725. So this will be kPa divided by p sub 1, that will be 100, no? Okay, so close parenthesis, this one. So I'm gonna raise this one to the power exponent of 1.3 minus 1 over 1.3. Then minus 1. Okay, close parenthesis. Okay. So let's try to use our calculator so we can solve now the values here. Okay. So we have the value of negative, no? Negative 5,023. So we have the unit here. So we're going to cancel out our units here. So this one and this one will be cancelled out. So this one will also be cancelled out. So we have the unit of kilonewton meter. So it is also expressed as kilojoule. So that will be, we have kilojoule. Sorry for that one. Kilojoule per minute. So we have the power for our, we have the work for our compressor. Now for letter B, so we have the heat rejected for our compressor. No? So for the equation of our heat rejected, so we have your Q. So for the process, that will be 1 to 2. Process 1 to 2 during the compression stage. Okay, so that will be equal now to the mass flow rate, 1 times the Cn. Then we have the change in temperature from 0.2 to 0.1. So let's try to evaluate the equation. So we don't have the mass flow rate given to the problem. We don't have the Cn, or the specific heat at a constant N. And also we don't have, given to the problem, the temperature too, that is also unknown. So we have 1, 2, 3 unknowns there in the problem. Okay. So remembering that in our ideal gas law, so we have uh, pressure times your volume. So that will be the mass flow rate times your R. Then we have the temperature at this point. So, okay. Now to get the mass flow rate, so we have to derive our equation. So that will be your P1 B1 divided by your R, and we have your T1. Now for your B1, okay, so let's try to plot this one to a PV diagram first so that we can understand. So usually we have the value for your P1 and we have your T1 to get our mass flow rate. Now for, so let's try to, so initially, for this one, if we're going to plot it in the PV diagram, so at point 1, so we have your point 1 here, then we're going to polytropically compress your air or nitrogen air to point 2, okay, going there. Then we shall have a discharge here going to point 3. Then we have the suction stroke here in the suction stage. So that will be the direction going there. Okay, then this one will be going there. Now, um, so this is now our PV diagram. So I'm going to uh, put the ano, the term call it yung mga values of here, or yung call it the representation of the problem. So for the values, okay. So we have now plot the PV diagram. So you will notice here we have the Boolean displays from 3 to 1, and we have the value. We have here the coverage for your B1. So starting from here, going down here, so that will be your B1. And we have also your B1 prime, which is the value of your 20, no? If you can still remember that one, that is will be your B1 prime, that will be 20 cubic meter. So this is the B1 prime, starting at the point 4. So point 4 going to 1, so that will be your B1 prime. Now, then for our, so this B3, so this is our B3 starting from here going there. Okay. Now, to get the value of your B1, so looking at the PV diagram, so our B1 is equal to BD plus B3. And we still remember that our B3 can be also expressed as from our clearance, if you can still remember this one. So we have your B3 divided with your BD. So we can express your B3 by means of multiplying volume displays multiplied by the clearance. So we have your B3, so equal to the clearance times the volume displaced. So we're writing an equation for your B1 is equal to BD, no, plus C times the volume displaced. And we can factor this one as volume displaced, that will be multiplied by 1 plus C for your clearance. And we can express our volume displaced in terms of volumetric efficiency. So from our volumetric efficiency, we have your NB. So that will be equal to B1 prime, since that is given to the problem, divided by your volume displaced. So we can express our BD now equal to, so this is can be equal to your BD is equal to your B1 prime divided by the volumetric efficiency, where our volumetric efficiency, no, so this is equal to the equation of 1 plus C minus C. So that will be the multiply to the ratio of P2 over P1. So this is raised to the exponent of 1 over n. Okay, so we can write our solutions here. So substitute natin yung values. So we have, so that will be 1 plus the value of your clearance. So whatever value of clearance there. So we have the value of clearance, which is 5%, no? So that will be 0.05 we have, then minus 0.05, then we shall multiply it by the ratio of your pressure. So P2, that will be 725. So we have 725 there, divided by 100. Okay. So I just have to move this one going down so that we can have an extra bigger space to compute. Then we close parenthesis this one and express it by the ratio of your exponent to 1 minus the 1.3. Now, so let's try to use our calculator. So we have now the value of your volumetric efficiency, which is equal now to 0.8205. So since now we have the volumetric metric efficiency, we can solve now the value of your BD. So our volume displays is equal now to your B1 prime divided by the volumetric efficiency, which is equal to 20 cubic meter per minute. Then it shall be divided by the volumetric efficiency, which is 0.8205. So this is now equal to 24.38. So this will be cubic meter per minute. So now that will be the value for volumetric efficiency. Now we can substitute now to get the value of your B1 since it's already being given now, already being solved. So we have now your B1, which is equal to, let's try to rewrite the equation. That will be BD. So that will 1 plus C. Okay. So our BD, that will be 24.38. So that will be cubic meter per minute. Then we shall multiply it by the 1 plus the clearance, which is 0.05. Okay, so we have now the value for your B1. So for your B1, it will be equal to 25, 25.6. So we have the units of cubic meter per minute. So from here, we can now solve the mass flow rate. So our mass flow rate now is equal to your P1 B1 divided your R, then T1. So for your P1, it will be 100. Okay, 100. So I'm gonna express this one in terms of kilonewton per square meter. Then I'm gonna multiply it by B1, which is 25.6. So that will be cubic meter per minute. Then shall divide it by your R of your air. So that will be 0.2967. Okay. Then, so this will be kilojoule per kilogram, kilojoule per kilogram Kelvin. Then it will be multiplied by the temperature, which is 310 degree Kelvin. So this is Kelvin. So cancel out our common units here. So we have Kelvin will be cancelled out. Square meter here. And so this is, let's try to express this one to kilonewton. Sorry, this is kilonewton meter. So I'm gonna cancel now this one, kilonewton. Cancel this one. Then we have your meter here, this one. So we have your minute. Okay. So we have now the mass flow rate for the units. Then we using calculator, so we have the value of 27.83. So that will be your kilogram per minute. Now, for the CN, remembering that our CN, that will be the equation for your CNs equal to CB. So that will be the multiply to the ratio of your K minus N divided by 1 minus N. So for the specific heat of the nitrogen at constant volume, so we have that value and we can find that one in a table. So for the specific heat at constant volume of nitrogen, so we have 0.7442. Okay, so this will be kilojoule per kilogram Kelvin. Then we shall multiply it to the ratio of your N, K. So the K for the nitrogen, that will be 1.399 minus 1.3. So that will be the value of N divided by 1 minus the 1.3. Okay, so for the value of your Cn is equal now to negative 0.2456. So that will be kilojoule, kilogram, Kelvin. Now, for the in order to compute the heat, so we have your equation for your heat. So that will be Q, no, our Q for the heat from point 1 to point 2. So that will be a mass flow rate times your point 1, which is already being solved in Cn. So we have the value now on that one. Then multiply by the change in temperature from T2 to T1. So we have the values for T1, the Cn, and the mass flow rate. Now what we don't have is the T2. So by using the PBT relationships, polytrophic, so we have your equation T2, T1 is equal to your P sub 2, P sub 1. So that will be raised to the power of n minus 1 over n. Okay. Then we shall have your T2, which is equal to T1. So that will be 310 Kelvin. Then multiply by the ratio of pressure. So we have 725 kPa. Then divided by the 100 kPa. Then raised to the power of 1.3 minus 1 divided by 1.3. So your T2 now is equal to 489. Okay, 489.7. So this will be in terms of Kelvin. So let's continue our solution since we have already the values. So we can compute the heat rejected during the compression stroke. So for mass flow rate, so that will be 27.83. So this will be kilogram per minute. Then we shall multiply this one by the value of Cn. That will be negative 0.2456. So this will be 2456. So this will be kilojoule, kilogram, Kelvin. Then multiply to the difference of 489 Kelvin, 0.7 Kelvin minus 310 Kelvin. Okay. So cancel out our units here. So kilogram will be cancelled out, Kelvin cancelled out. Okay. So we have wait, now for the lastly we have your volume displays. So for letter C, so we're looking now for the for the letter C, we're looking now the bore and the stroke for 150 RPM. And we have your ratio of L over D, that will be the length, and the bore, which is 1.3. Now for the given, we have for the calculation, we have your volume displays. So that will be pi over 4. So this is times the diameter squared, then you have multiplied by the length, okay, for the Boolean displays. Now we're going to substitute. We have here your pi over d, pi over 4. So for the diameter squared, then we shall write your L, okay. So since we have earlier, so we have the ratio of your L over D. So your L over D, okay, is equal to 1.3. So we can express this one for your L. So your L will be um, equal to 1.3 times D. So I'm going to substitute that for the value of L. So we have 1.3 times D, okay? And for your now for your value of your N, so usually this will be your RPM since we are in. So take note. So the problem state it is a twin cylinder double acting. So our N that will be is equal to your RPM times 2. Okay, so that will be for the value of your N. Okay, so that will be 100. How much is that? 150 revolution per minute. So that will be since it is double acting, so it will be multiplied by 2. So we shall substitute the value of N that will be um so that is 150. Okay, 150 rev per minute, no? So that will be multiplied by 2. Since also, if you will notice here in the problem, so we have stated here it is a twin cylinder. Okay, so it means it has two cylinder that is double acting. Okay, so again, we're going to multiply again this one by another multiply again by 2 again, not this one. So our Boolean displays, so multiply this one by the whole equation. So we have 612.6. That will be D cubed. So that is cubic meter per minute. Okay. Okay, so that will be. So now, from the problem, we also have the value of your Boolean displays. So, okay. So our volume displays, it will be 24.38. So, so this will be 24.38. That will be cubic meter, no, per minute. So it is equal now to 612.6 d cube cubic meter per minute also. Okay. So we have now 24.38. So to get the bore, so we have your D to the 24.38 divided by 612.6. So that will be cube root of that value. So we have now the value of your D is equal to, so it will be equal to 0.3414 meter, or let's say that will be 34.14 centimeter. Now for the length of stroke. So what will be the length of stroke? So we have this one. Length of stroke that will be 1.3 times their D. So we have 1.3 multiplied by the diameter, which is, let's say this is will be 34 now, 34.14 centimeter. So we have value of 44.38 centimeter for the length of stroke. Okay. So looking at the summary of our solution. So I'm going to zoom out this one to take an overview of our solution. So starting from here, going down here. So we start. So let's start a recap. So work. So that is already expressed in negative since we supply the work on the system. And also you will notice the values of here are also given to the problem, so we can easily compute. Now for the heat rejected, that will be from point 1 to starting from here going there. So that will be the polytropic compression. So we have the mass flow rate times Cn, and we have the change in temperature. So we get to get the mass flow rate, so we use initially the ideal gas law, that will be PVMRT, so we can get the mass flow rate. Then for the volume 1, so that will be initially displaced on the PV diagram. So take note of this one, so try to remember this one on the PV diagram, so you will not be lost during the solving of your equation, solving of the problem. So you will take note that the B1, it will be from this side, so where it means that there is no clearance. Then your B3, so it is also from here, from point 3, so starting from the 0 here going to 3. Then your volume displaced is starting from point 3 going to B1, and our B1 prime, so it will be the volume during the volume of air that is being drawn in or sucked in during the compression, during the suction stroke. So that will be from starting from B4 to B1. Now we have here, so we have your B1 is equal to BD plus your B3. Okay, so initially that we have that value. Then we try to express this one. Okay, so looking at the overview of our solutions. So okay, going down and going here. So